Alright, so in this particular video, it asks us at what altitude above Earth's surface is the acceleration due to gravity equal to g over 6. So 1/6 of the acceleration due to gravity at the surface, okay? So I want to point out it says altitude, aka height, here in the diagram. H is what we're looking for, and it says above the surface, so we have to measure it from the surface to the top. And it says acceleration is 1/6 of g, so same thing as saying g over 6. So here in the diagram, I have drawn for you a, or acceleration is 1/6 of the acceleration due to gravity. All right, so let's focus on finding h real quick. The first method is what I like to do. You don't have to do it, but I like to do this before and after type scenario where you don't have to do a lot of calculator work. So here my first work is at the surface. The second side is the altitude or elevation or height, whatever you want to call it. Here, I know the generic function for acceleration due to gravity is g me over r squared, and this particular function is the expression to find g anywhere. However, I do want to point out that because I'm using r in the denominator, it implies that this particular acceleration is at the surface of the planet, hence it's on the left side of my work here. Okay, so r in the diagram is measured from center of the earth to the surface of the earth. So that's my reference point. Well, it doesn't want us to find g at the surface because we don't know that. It wants us to find h, in which acceleration is 1/6 of g, right? So let's go ahead and set up the right side. I can set up the same function, acceleration due to gravity at some altitude, which is equal to g m earth over d squared. So on the right side, that's different than the left side. This left side is just the radius of the earth. On the right side is d, whatever d is. So d in this case is defined as center to center. Okay, so the center of the earth in this diagram to the altitude where it wants us, where g is over 6. That altitude from the surface of the planet is just called h. So this is what I'm going to call d. Okay, the distance from center of the earth to where the reference point is. I'm just going to call this d, and as you can see, d in this case is r plus h. So once I find d, I can subtract d from r, and then I just know h. So I want to focus on finding d real quick. So here in my work, g altitude is given to us as g over 6. So I'm just going to do a quick substitution to get rid of the g altitude term. So generically, g altitude is g m e over d squared, but here I know g altitude is given as g over 6. And then the function here on the right side gets carried down. But I need to find d. I need to find d because once I know d, I can just subtract it from the radius of the earth, and that is my height. Okay. Therefore, I want to do a little algebra switcheroo. D squared is in the denominator on the right side, so I want to move it up to the left numerator. But at the same time, I'm going to move the g down, and then I'm also going to move the 6 up to the right. Okay. So therefore, I have d squared is equal to 6 because I want to move the 6 on the left denominator up to the right numerator. So that's going to be 6 GME, and then the acceleration due to gravity at the surface of the planet would just be cross multiply here, or divide both sides by g, however you want to say it. That's going to be g in the denominator. So as you can see here, we know what excuse me. We know all these values, right? We know all these values. We know what g is, we know what m is, we know what little g is. Except I don't want to plug in calculator work. What I want to do is quickly substitute out g. Okay, I know the function for g is gm earth over the radius of earth squared. So I'm just going to plug it out, or I'm just going to substitute it out. So the numerator stays the same, except for g, I'm just going to write in parentheses here g m earth over r squared. And because in this particular process, the right side is being divided by a fraction, which implies that you need to multiply it by the reciprocal. So on my next work here, I kept the numerator the same, which is 6GME, which is right here, 6GME. But the denominator is being flipped because I need to multiply by the reciprocal. So r squared is going to go on top now, and then gm earth is going to go on the bottom. But if you're paying attention, gme numerator and gme in the denominator is going to get canceled out. So therefore, I have a statement that's pretty straightforward. I have d squared is equal to 6r squared. Well, I'm trying to solve for d, and this is d squared. So to get d by itself, we need to square root both sides. So therefore, you need to take the square root of 6 and r squared. Well, the square root of 6, I just broke it up into two pieces here. It's just radical 6. But then the square root of r squared, well, the radical sign and the exponent 2 cancels out. So that would just leave us with r. I wrote it like this because this is the square root of 6 times r. So it's important that you write this properly, okay? The square root of 6 ends up just being about 2.45. And therefore, 2.45 times r is just 2.45r. So back to my diagram. I know what d is. I just found what d is. D is 2.45r. And just by basic arithmetic, well, the radius of the planet is r. The height is above the surface. So to find h, I would take the total distance from center to where the reference point is, subtract it from r. So therefore, h would just be the leftover. So in this case, I have 2.45r, subtract r, which is 1. So 2.45 minus 1 is 1.45, 1.45r. So if you keep it up here, I have the statement h is equal to 1.45r. Okay. But I know what r is. R is given the statement. The radius of the planet is a constant. It's 6.36 times 10 to the 6 for Earth. All right. So therefore, I can just substitute out r for the radius of the Earth, which is given. And if I plug it all in my calculator work, I should get a value of about 9 million meters. About, right? You have all this 222 as well. But on the big scale, you have about, well, it's about 9 million meters. All right. So that is the answer for this particular problem if you choose this approach. The other way to do it is just plug and chug, right? We know the function for g altitude, or the acceleration due to gravity at this altitude, whatever altitude is simply by plugging in g, the universal constant, times the mass of the planet. But then d here is measured from center to center. So you notice in the denominator, I have r plus h in parentheses. Well, that's because if you look at this diagram properly, if you measure from the center of the Earth to the surface of the Earth, that's already a radius of r. But from the surface up to where the reference point is, that's an additional h. So it would be r plus h, hence center to center. Well, in that case, the denominator needs to be in parentheses r plus h. So this is where if you're not careful with parentheses or the usage of parentheses, you might screw your work over, okay? Well, I know for a fact, right, that this is r plus h. So therefore, I can plug in g altitude. And g altitude is given as g over 6. So I'm just going to go ahead and substitute out like I did in the last process. G over 6. Except, you notice here, I'm looking for h, right? Ultimately, the question is looking for h. It says altitude. Well, I know a lot of terms already, but the only thing I want to do here differently compared to other things, some people, is that I'm just going to go ahead and solve for h algebraically first before I do all my substitution for the values. So this is r plus h squared. This term is in the denominator that I'm circling, but h is in the denominator. So to get h in the numerator, I want to cross multiply. So I want to bring the whole quantity up to the left. I want to move g down to the right denominator, but at the same time, I want to move the 6 to the numerator. Okay, so therefore my work looks like this. All right, I want to bring the whole denominator, r plus h squared, up to the top left. I want to move g down to the bottom right, because that's what happens when you switcheroo or divide both sides. And then 6 is going to go up to the top, hence there's 6 there. But I notice here h is inside the parentheses, so it's not by itself yet. But this whole bracket, this whole term in parentheses being square. So the next algebraic step to do is to take the square root. Right? Taking the square root of both sides, get rid of this exponent 2 on the left side. Therefore, it puts everything on the right side underneath the radical. Well, I almost have h by itself. H is almost by itself, right? You have this r, but that's easy. To get rid of r, you would just subtract. This is a positive r, so I'm going to subtract both sides by r, or I like to say move this r to the right side of the equal sign and you change the sign. So therefore, h is equal to this whole radical minus r, right? So if you're keeping up with the algebra, good. If not, maybe rewind and play it. So now that I have the whole function I say for h, I can now substitute in values. I like to do my values at the very end. Well, 6 is just a constant. I want to carry that down. G is the universal constant, which you should know by now. 6.67 times 10 to the negative 11. The mass of the Earth is given in the statement here, right? It's 5.98 times 10 to the 24th kilogram, which I substituted there. And all this underneath the radical sign. And then G is 9.8 meters per second squared. So you notice here, everything in the underneath the radical is already substituted out. and then it says minus r. Well, I know what r is. R is 6.367 tenths of the 6 meters. So if you simplify everything underneath the radical, you should get, right, a value of 1.56 about times 10 to the 7th. So if you punch all this stuff in your calculator and then take the square root of it, you should get about 1.56 times 10 to the 7th. And then you're still going to subtract it from r, which is 6.36 times 10 to the 6. So if you take the difference here, you should get about 9.27 times 10 to the 6, which is essentially the previous answer. I know the last answer was 9,222,000. Here we have 9,227,000. Give take a little bit of rounding based on our usage and methods because it does involve decimal. But on the big scheme of thing, it's about 9.2, or 9.3 times 10 to the 6 meters, which is essentially the same answer. All right, I hope that helps. Stay nerdy, don't be white.